I was extremely disappointed in the lack of angry comments on my previous video about the Basel problem, in which I promiscuously used a Divergent series to provide a non-rigorous answer to the Basel problem. What I'd like to do in this video is briefly share with you some observations that I've made in the ways in which the Divergent series connect with the Fourier series in a rather bizarre way. Let me get right into it, and what I'll do is first remind you that the sum of a geometric series, which is given by, for example, a naught plus a naught times r plus a naught r squared, and so on, where each term gets multiplied by r to form the next term, that if this series converges, the value that it converges to is given by a naught divided by 1 minus r. An easy example, a quite familiar example, is when a naught is equal to 1, and when r, which is also called the common ratio, is equal to 1/2, in which case I get the following geometric series. 1 plus 1/2 plus a fourth plus an eighth, and so on, is equal to, just following the formula, 1 over 1 minus 1/2, which is equal to 2. And this is a convergent series in the usual sense. And in general, such geometric series only converge when the absolute value of r is less than 1. If you were to stick in r is equal to 1, you would get a divergent series. What I'm going to do is take the special case when a naught is equal to 1 and when r is equal to x. So I have 1, I multiply by x to form the next term, plus x, multiply by x again to form x squared, then x cubed, and so forth. And according to the formula, this is going to be equal to 1 over 1 minus x. As I said before, these geometric series only converge when the common ratio r has an absolute value of less than 1. In our case, the common ratio was x, so this infinite series is only convergent when the absolute value of x is less than 1. Now we recognize that fact. Now we're going to go ahead and break the rules. What I'm going to do is make the substitution x is equal to e to the I theta. Now if you know a bit about complex numbers, this e to the I theta is always located on the unit circle when you draw this in the complex plane. So in fact the magnitude of x, no matter the choice of theta, is always equal to 1. But since we are promiscuous individuals, we are going to go ahead and make the substitution anyway. So let's make that substitution. I have 1 plus e to the I theta plus e to the I 2 theta, just squaring that thing right there, plus e to the I 3 theta, and so on, is equal to 1 over 1 minus e to the I theta, which, if you use Euler's formula, you can show that this thing is equal to, just after doing some simplification, to 1/2. 1/2 is going to be the real part of the complex number, and the imaginary part is going to be 1/2 cotangent of theta over 2 times I. Now for this demonstration, or my observations, I'm only going to need the real part here, this 1/2. Now, if this complex number is going to be equal to this complex number, whatever complex number is given by that infinite series, the real part of this left-hand side has to match up with the real part of the right-hand side. So let me write down the real part of the left-hand side. So 1 is all real, so just have 1 right there. Now e to the I theta, what's the real part of that? By Euler's formula, that's plain old cosine theta. And for this one, e to the I 2 theta, the real part is going to be cosine of 2 theta. Then for this one, hopefully you're seeing the pattern, plus cosine 3 theta, and so forth, is somehow equal to 1/2. And now I'm going to subtract 1/2 from both sides. So I get the equation 1/2 plus cosine theta plus cosine 2 theta plus cosine 3 theta, and so forth, is somehow equal to 0. In a few minutes, assuming you haven't run screaming out of the room already, I'll show you some animations of the Fourier series and these infinite sums. But what I'd like to do is one last maneuver. What I'm going to do is make another substitution, which is going to be theta is equal to x plus pi. And let's see what happens when I do that. I have 1/2 plus cosine of x plus pi plus cosine of 2x plus 2 pi plus cosine of 3x plus 3 pi, and so forth, is equal to 0. Now, let's look at the effect of this addition of these multiples of pi to the cosine wave. Now, adding pi, in terms of what it's doing to the cosine wave, it's shifting the wave leftward by pi units, which if you draw that out, that's going to have the effect of negating the wave. So I come to cosine of x plus pi is just equal to cosine x. Now, what is the effect of adding 2 pi to the argument here? Now, that's just one complete revolution around the circle. So cosine of 2x plus 2 pi is simply equal to cosine of 2x. And now for this wave, what happens when I add 3 pi? Well, that's just the combined effects of doing this and this, which is going to have the effect of negating the wave. So I'm going to have minus cosine 3x. And hopefully you're seeing this pattern here, that the substitution is going to generate this alternating series now. So now the next term is going to be plus cosine 4x. The next one will be minus cosine 5x. And it's an infinite series, and that's still equal to 0. The last thing I'll do with this infinite series is do a little bit of rearranging. I'm going to write cosine x first. Then I'm going to have minus cosine 2x plus cosine 3x minus dot 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 is equal to 1/2. And hopefully you can see that this is just a rearrangement of this equation here. And now what I'd like to do is show you an animation in which I plot these waves when I add more and more terms of this infinite series. So first I'm going to plot cosine x, then I'm going to plot cosine x minus cosine 2x, then I'm going to plot the first 3 terms, then the first 4 terms, and so forth, and let's observe what happens. What you're going to see me do here is add up the first 50 terms of that series that I just mentioned, moving in increments of 5, and let's see what happens. And hopefully what you're noticing here is that we get these peaks starting to develop here, and they get larger and larger as we add more terms. And these peaks are repeating in regular increments. It turns out there's a very good reason for the location of these peaks. This is actually at negative pi, this is at pi, this is at 2 pi, and the next one's going to be at 3 pi, and these peaks repeat off to positive and minus infinity. In addition to the peaks, we get these regions here and here, which seem to vibrate in a very bounded manner. That is, they don't oscillate too wildly. And let me zoom in to one such region here. And what I'd like you to notice here is if you had to eyeball what the average value of these oscillations would be over this interval here, it seems like these oscillations are oscillating about 1/2. That is, if you kind of follow this trajectory here, the middle of this trajectory seems to be right about there. And you can see its y value is approximately 0.5. So this is just an interesting observation. I don't have any rigorous arguments to show you. But it's quite interesting that this thing came out to be 1/2, which is what that divergent series was suggesting to us. What I'd like to do now is now show you how we can actually derive a bona fide Fourier series from this seemingly ridiculous looking series. And the way I'm going to do that is simply integrate both sides of the equation from 0 to some other variable t, 0 to t, with respect to x. Now, what is the antiderivative of cosine? That's going to be sine x. And just using the fundamental theorem of calculus, I'm going to get sine t minus sine 0, which just gives me sine of t for the integral of that first term. Then the second term, I'm going to get something very similar. It's going to turn out, if you do all the calculation, it's going to be sine 2t over 2 plus sine of 3t divided by 3. The next term, predictably, would be sine 4t over 4, and so on, is equal to the integral of the right-hand side, which that's an easy integral. That's just going to be t over 2. And now, let me multiply both sides by 2, so that I get the equation t is equal to 2 times exactly what I had before, which is sine t minus sine 2t divided by 2 plus sine 3t divided by 3, and so on. Now this is interesting, and I'd like to show you an animation of what this infinite series generates in the same method as before. I'm going to successively add on more and more terms. And we should notice that this right-hand side is suggesting that this infinite series is in some way equal to a line, because when I plot the equation, for example, y equals t, that's just a plain old line. If I plot like this, that's just a plain old line. And here's the animation as I add on more and more terms, going up to about 50 terms, again moving in increments of 5. And hopefully what you're seeing here is that this middle portion of the wave on the interval minus pi to pi looks pretty damn similar to a line, as was suggested by that divergent series. Moreover, you can see that this waveform, this linear looking waveform, ends here at around x equals pi. It then dives back down only to repeat the same waveform. And you can see this waveform is continuously repeated. And it turns out this is the calling card of a Fourier series. That is, the Fourier series work like this. They have a waveform over a certain interval, and then that waveform gets repeated off to plus minus infinity. And now let me take the data cursor and show you some of the data values here. And as I scroll through some of the data points, you can see that the x and y values are more or less the same. They're pretty damn similar, which suggests that if this thing is a line, that it's the line y equals x, or in my variables it was y equals t. After having seen that we can generate lines through this infinite series of sine waves, one may very naturally wonder whether we can generate other shapes as well. Now, you can think of the line as a first order polynomial. It's t to the first power. So one may wonder if we can generate the next highest order, which would be t squared, also known as a parabola. Now, a naive approach would just be to square both sides. So I square the left-hand side, I get t squared. When I square the right-hand side, I get 2 squared, which is going to be 4. And then I just square this whole infinite series. A naive approach, and admittedly a promiscuous approach since I'm squaring an entire infinite series. But let me show you in the animations what happens when we plot more and more of these terms. That is, I choose, let's say, the first 3 terms, compute the sum, then square it, of course multiply by 4, and then plot it, just as I did before. Let's see what happens. Let's have a look. Again, the first 50 terms being plotted in increments of 5. And hopefully you're seeing as I add more and more terms that I do indeed get these paraboloid looking shapes here. Again, on this interval minus pi to pi, and then that same shape, the parabola, gets repeated in the next chunk, the next interval, which would be pi to 2 pi. And to hopefully convince you that this paraboloid looking thing is indeed the parabola x squared or t squared, let me have a look at the actual data points. So let me go to, for example, x equals 2. Now if it's a parabola x squared, the y value should be pretty close to 4. And you can see that it is for the first 50 terms. It It generates something pretty close to 4. Let's go up to, let's say x equals 3. In the noisier region, deviate slightly. We know that 3 squared should be 9, but it's not too close to 9. Let me go to yet another value, which is x equals 1. 1 squared is obviously 1, and the y value is pretty close. At this point, why restrict ourselves to squaring that equation for the line? Why not cube it? So when you cube it, this is what happens. Now in this graph, I'm going up to, I think, 300 instead of the 100 as before. And hopefully what you're seeing is that on this interval, minus pi to pi, we do get these waveforms that appear to be cubic equations. And again, this is just simply cubing that equation for the line that we first got. And let me see what's going on with this data here. So if this is the equation x cubed, when I go over to x equals 2, I should get a y value pretty close to 8, because 2 cubed is 8. And that's indeed what happens. You get 7.934. And if I were to go over to x equals 1, 1 cubed is 1, and I do get a y value close to 1. One last slightly goofy thing that I'll show you is what happens when you start combining these graphs. That is, we have the equation for a line. We plotted that line first. Now we plotted the cubic. So we could take different combinations. We could take the equation for the line and then subtract away the equation for the cube divided by 3 factorial. Now I do that because those are the first 2 terms of the Taylor expansion for sine x. And this is what you get when you animate this. As I said, it's slightly goofy because you would never calculate the sine function in this way because you're using sines to calculate it. But nonetheless, you see that these sine waves are starting to develop here. Just an interesting observation. As I said, slightly goofy. I should like to thank all of you guys for making it to the end of the video, and I highly encourage you to subscribe to my channel if you enjoyed this video, and stay tuned for hopefully more interesting videos. And I'd also like to extend a thank you to my already existing subscribers. I enjoy talking with all of you guys, and I'd also like to ask you what other math and science topics would you like to see more of on this channel? Especially if there's some topic in higher math that seems esoteric or convoluted. I'm always open to suggestions. And I would also ask a favor of you guys to share this channel and the videos with your fellow math nerds. Thanks again for watching.